The first topic that we're going to study is the condition of stability, and this is going to be a fairly simple concept, but it's one that has profound importance in the rest of the chapter. The question that we're going to be asking here is as follows. Imagine that we have a piece of ice floating on top of a glass of water. The question that we're asking here again is, well, suppose that you have a tiny little bit of the ice turning into the liquid. And this tiny little bit of the ice is infinitesimal. We're going to call it a differential of n. The question that we ask is, well, in that process of that tiny little piece of ice turning into the liquid, is that process spontaneous, or does it occur at equilibrium, or is it not spontaneous? Okay, this process takes place at constant pressure and temperature, and that means that we can use the Gibbs energy as a criterion for spontaneity. So what we're going to be doing is calculating the Gibbs energy before the process takes place, the Gibbs energy after the process has taken place, and then the difference between those two is going to tell us what delta G is, or differential of G in this case, because that's a small infinitesimal amount. And then from the sign, we will be able to tell whether this is spontaneous or not. Okay. So before the transformation takes place, we can say that the total Gibbs energy that we have initially is just going to be the sum of the Gibbs energy of one of the phases plus the sum of the Gibbs energy of the other phase, the ice and the liquid. Right, so what is the Gibbs energy of the ice? Well, the Gibbs energy of the ice is simply going to be the amount of ice that you have, number of moles of ice, multiplied by the molar Gibbs energy of the ice. Right? That is the contribution per mole of ice. You just multiply it by however many moles of ice you have, and that will give you the total Gibbs energy of just the ice in that system. Well, you also have the liquid, and that means that you also have to reckon with the Gibbs energy of the liquid. So for the liquid, we will have the number of moles of the liquid multiplied times the contribution per mole of the liquid. Okay, that's before the process takes place. Now, after a tiny little bit amount of ice turns into the liquid, then the final Gibbs energy can be defined as follows. That's the final. We're going to have the same equation, but notice that the number of moles of the ice and of the liquid have changed. You have a little bit less of ice and a little bit more of ice, right? So we can rewrite that this is going to be equal to the number of moles of ice that you had initially minus the tiny little bit that has melted into the liquid, multiplied by the contribution per mole of the ice. Okay. And then for the liquid, we have that the number of moles that you have after the process has taken place has increased a little bit by an infinitesimal amount. So you have that this is going to be equal to the number of moles of the liquid that you had plus a tiny little bit more that has been formed when the ice has melted. And you have to multiply this by the contribution per mole of the liquid. Okay, so that is our initial Gibbs energy, that is our final Gibbs energy. If we subtract these two, then we will get final minus initial. That will be the change in Gibbs energy in the process. Okay, so let's do that. If we subtract these two, you get differential of G, okay, which is the change in the Gibbs energy. Okay, notice that this term that you have right here is going to cancel out that term, and this term is going to cancel out that term. So only the terms that have differential of n's will survive. Okay, so if we write that down, it's going to be differential of n multiplied by the molar Gibbs energy of the ice plus differential of n multiplied by the molar Gibbs energy of the liquid. Okay, that is the result. Now if we take common factor of the differential of n, okay, then we get that this is going to be equal to the molar Gibbs energy of the liquid minus the molar Gibbs energy of the ice. And now we ask the question, under what conditions is this differential of G going to be negative, which will signal that the process will be spontaneous? All right, well, this number is always going to be positive. That's just the change in moles, right? So this will be 0.1 moles or 3 moles or whatever it is, but it's always positive. Now that means that the only way to make this negative is if this parenthesis is negative. And how do you make the parenthesis negative? Well, the parenthesis is going to be negative whenever this term is greater than that term. Okay? So, in other words, when the molar Gibbs energy of the phase that you're departing from is greater than the molar Gibbs energy of the phase that you're turning into, then the process will be spontaneous. There's another way to say this. Notice that the process will be spontaneous is that if the phase that you're turning into has a lower molar Gibbs energy than the phase that you're starting from. Okay, so notice how the molar Gibbs energy determines the stability of a process. If this is a vaporization or a protein denaturation or any process that you can think of, the phase transition is going to be taking place if under the conditions of pressure and temperature that you're working at, you actually have that the molar Gibbs energy of the final phase, the phase that you're transforming into, is lower than the molar Gibbs energy of the phase that you're starting from. Again, that's very important, and again indicates that systems move to minimize the molar Gibbs energy, at least when we're working with pure substances. That's the condition for stability.